Welcome to this coding problem walkthrough. In this session, we'll be tackling LeetCode problem number 326, power of 3. We'll explore the problem statement, analyze various approaches, and walk you through the solution step by step. Let's dive in and get started. The power of 3 problem, LeetCode number 326, is a simple yet interesting challenge. The task is to determine whether a given integer, n, is a power of 3. In mathematical terms, an integer n is considered a power of 3 if there exists another integer, x, such that n equals 3 raised to the power of x, or n equals 3 caret x. If this condition holds true, the function should return true. Otherwise, it should return false. The input to this problem is a single integer, n, which is of type integer, and the output is a Boolean value, true if n is a power of 3, and false if it is not. This simplicity in the input and output format makes the problem approachable, yet the challenge lies in efficiently determining whether the condition is satisfied for any given integer. To understand the problem better, let's look at some examples. In the first example, the input n is 27. The output here is true because 27 can be expressed as 3 raised to the power of 3, or 3 by 3 by 3. Since this satisfies the condition for being a power of 3, the output is true. In the second example, the input n is 0. The output in this case is false. This is because 0 cannot be expressed as any power of 3, as raising 3 to any exponent will never result in 0. These examples illustrate both positive and edge cases for the problem. Next, consider another set of examples. When n is 9, the output is true because 9 can be expressed as 3 raised to the power of 2, or 3 by 3. This satisfies the condition for being a power of 3, so the output is true. On the other hand, if n is 45, the output is false. That's because 45 cannot be expressed as 3 raised to any integer power. These examples highlight how the solution must determine whether a number can be written as 3 caret x or not, for both small and larger values of n. Now let's review the constraints and edge cases for the problem. The input n lies within the range of signed 32-bit integers, from -2 billion to +2 billion. This means our solution must handle both very large positive and negative values. If n is 0, the output must always be false, as 0 cannot be expressed as a power of 3. Similarly, for negative numbers, the output is always false, since raising 3 to any integer power will never yield a negative result. Lastly, the solution must be efficient, especially for large values of n, ensuring it works within the constraints of the 32-bit integer range. These considerations are important to keep in mind as we design and implement the solution. To determine if a number n is a power of 3, we can consider multiple approaches. First, the brute force approach uses iterative division. The idea here is straightforward. Since powers of 3 are produced by repeatedly multiplying 3, we can repeatedly divide n by 3 to check if it eventually reduces to 1. If n is less than or equal to 0, we know right away it cannot be a power of 3, so we return false. Otherwise, we continue dividing n by 3 as long as it remains divisible. If the final result is 1, we return true, otherwise, it's not a power of 3. This approach has a time complexity of O log_3, n, as the number of divisions is proportional to the logarithm of n in base 3. It also uses constant space, making it memory efficient. However, one drawback is that for very large numbers, the repeated division might become computationally expensive, even though the process itself is simple to implement. An optimized approach involves leveraging the maximum power of 3 within the range of a 32-bit signed integer. The largest power of 3 that fits in this range is 3 to the power of 19, which equals 116,226,1467. The key insight here is that any power of 3 must be a divisor of this value. Based on this, the algorithm is remarkably simple. First, pre-compute the maximum power of 3, which is 116,226,1467. Then, check if n is greater than 0 and if the maximum power of 3 is divisible by n without leaving a remainder. If both conditions are satisfied, n is a power of 3, and we return true. Otherwise, it's not, and we return false. This approach is extremely efficient, with a time complexity of O(1), since it involves only a couple of constant operations. It also uses constant space. The trade-off here is that it relies on pre-computing the value of 3 to the power of 19, but this is trivial since the range of n is well-defined and doesn't change. Another alternative approach involves converting the number n into its base 3 representation. The intuition behind this is that in base 3, any power of 3 will always have the form 10, 0 foot, a single 1 followed by only zeros. To implement this, we convert n into its base 3 form and then check if it matches this pattern. While this method is mathematically interesting, it's less efficient than the previous approaches. The conversion to base 3 takes O log underscore 3 n time, and storing the base 3 representation also requires O log underscore 3 n space. These additional computational and memory requirements make this approach more complex and slower compared to the earlier methods. As a result, while it works, it is not the most practical solution for this problem. The optimized approach, which uses the maximum power of 3, is the preferred solution for this problem. It stands out because of its efficiency, simplicity, and robustness. With a time complexity of 1, it is the fastest method among the three. The logic is straightforward and requires only a couple of checks, making it easy to implement. Additionally, it works seamlessly for all valid inputs without requiring iterative computations or conversions. The only limitation is the reliance on the pre-computed value of 3 to the power of 19, but this is a minor consideration given the constraints of the problem. Comparing the approaches, the brute force method, while simple, is slower due to repeated divisions. The base 3 conversion method is even less efficient and more complex due to the overhead of converting and analyzing the base 3 representation. The optimized approach provides the best balance, making it the ideal choice for solving this problem effectively. In this problem, we need to determine if a given integer, n, is a power of 3. Mathematically, this means there should exist some integer k such that 3k equals n. To solve this, we use an iterative division approach. The intuition behind this method is simple: powers of 3 are formed by repeatedly multiplying 3, resulting in values like 1, 3, 9, 27, and so on. So, to check if n is one of these powers, we can reverse the process by repeatedly dividing n by 3, as long as it remains divisible. Here's how it works step by step. First, we perform an initial validation. If n is less than or equal to 0, we can immediately return false because powers of 3 are always positive integers. Next, we enter a loop where we divide n by 3 repeatedly, as long as n is divisible by 3. This step effectively reduces n by removing factors of 3 one by one. Finally, we check the result after the loop. If n has been reduced to 1, it means n is indeed a power of 3, so we return true. Otherwise, we return false, indicating that n is not a power of 3. Now, let's analyze some key insights about this approach. First, why do we stop at 1? If n is a power of 3, dividing it by 3 repeatedly will eventually reduce it to 1, since 3k divided by 3 repeatedly will reach 3 0, which equals 1. If n is not a power of 3, at some point during the division process, the remainder will no longer be 0, causing the loop to stop prematurely. This means n cannot be reduced to 1, and we can safely conclude it is not a power of 3. Additionally, we need to consider edge cases. For instance, if n is 0, it's not a power of 3 because powers of 3 are strictly positive, so we return false. Similarly, negative numbers cannot be powers of 3, so we return false for any n less than 0. On the other hand, if n is 1, we return true because 1 corresponds to 3 0, which is a valid power of 3. For very large values of n, the algorithm remains efficient because the number of iterations is proportional to the logarithm of n in base 3. This gives us a time complexity of O log underscore 3 n, which is manageable even for large inputs. As for data structures, this algorithm is very space efficient. The input is a single integer n, and we don't use any additional data structures beyond modifying n itself in place. The output is straightforward, a Boolean value indicating whether or not n is a power of 3. Here's how the code begins. We validate the input and then proceed to the iterative division step. In the iterative division step, we use a loop to repeatedly divide n by 3 as long as n is divisible by 3. This is done using the operation n // equals 3, which performs integer division and updates n in place. Once the loop exits, we perform the final check. If n has been reduced to 1, we return true since it confirms that n is a power of 3. Otherwise, we return false. While this approach is efficient, there are optimizations we can consider. One optimization involves pre-computation. If we know that n falls within a specific range, we can pre-compute all powers of 3 within that range and store them in a set. Then, checking if n is a power of 3 becomes a simple set membership operation, which has O(1) time complexity. Another optimization uses a mathematical property. The largest power of 3 that fits within a 32-bit integer is 3*19, which equals 1,162,261,467. If n is greater than 0 and this largest power of 3 is divisible by n without a remainder, then n must be a power of 3. This eliminates the need for iterative division entirely. Here's the code for this mathematical check. It simply verifies that n greater than 0 and 11622614667% n equals 0. By leveraging this property, we achieve a highly efficient solution that works in constant time for valid inputs. This solution determines if a given integer n is a power of 3 by using an iterative division approach. Here's a step-by-step breakdown. 1. Edge case check. The first line checks if the input n is less than or equal to 0. Since powers of 3 are always positive integers, any non-positive input immediately returns false. 2. Iterative division. The while loop checks if n is divisible by 3, n%3 equals 0. If divisible, n is divided by 3 using integer division, n // equals 3. This process continues until n is no longer divisible by 3. 3. Final check. After the loop, if n equals 1, the function returns true, indicating that n is a power of 3. Otherwise, it returns false. This approach ensures that only numbers that can be reduced to 1 through repeated division by 3 are identified as powers of 3. It handles edge cases such as n equals 0, n less than 0, and non-power of 3 values efficiently. The time complexity is O log 3, n, since the number is divided by 3 in each iteration, and the space complexity is O(1). This makes the solution both optimal and straightforward. This is the Java implementation of the power of 3 problem from LeetCode. The logic follows the same approach as the Python solution. It checks if the input number is a positive integer, then iteratively divides it by 3 as long as it is divisible. If the number eventually reduces to 1, it is confirmed as a power of 3. Key differences include Java's strict type declarations and the absence of Python's dynamic typing. In this walkthrough, we'll solve the problem of determining if a given number, n, is a power of 3. Let's begin with an example where n equals 27. First, we check if n is less than or equal to 0. Since 27 is greater than 0, this condition is false, and we move forward. Next, we enter the while loop, which will keep running as long as n is divisible by 3. In the first iteration, 27 is divisible by 3, so we calculate n equals n//3, resulting in n equals 9. We then check the loop condition again, and since 9 is still divisible by 3, the loop continues. Dividing 9 by 3 gives us n equals 3. Repeating this process once more, 3 divided by 3 results in n equals 1. Now, when we check the loop condition, 1 is not divisible by 3, so the loop stops. Finally, we check if the value of n is exactly 1. Since it is, we conclude that 27 is indeed a power of 3, and the function returns true. This makes sense because 27 can be expressed as 3 raised to the power of 3. Now, let's look at 2 more examples to solidify our understanding. For the second example, n equals 0. The first step is to check if n is less than or equal to 0. Since n equals 0, this condition is true, and the function immediately returns false. The reasoning here is simple: powers of 3 are always positive numbers, so 0 cannot be a power of 3. Moving to the third example, where n equals 45, we start by checking if n is less than or equal to 0. Since 45 is greater than 0, we proceed. Entering the while loop, we see that 45 is divisible by 3, so we calculate n equals n//3, which gives n equals 15. Checking the loop condition again, 15 is still divisible by 3, so we divide again, resulting in n equals 5. At this point, re-evaluating the loop condition shows that 5 is not divisible by 3, so the loop terminates. Finally, we check if n equals 1. Since n equals 5, the function returns false. This makes sense because 45 cannot be expressed as 3 raised to any integer power, so it is not a power of 3. To analyze the time complexity of the given code, we start by examining the loop where the input number n is iteratively divided by 3. In each iteration of the while loop, the value of n is reduced by a factor of 3. This means that the loop will continue until n either reaches 1, if it is a power of 3, or becomes a number that is no longer divisible by 3. The number of iterations in this loop directly depends on how many times n can be divided by 3, which is equivalent to the largest power k such that 3 raised to the power of k is less than or equal to n. Mathematically, this translates to approximately log_3 n iterations. Beyond the loop, the operations performed, such as checking if n%3 equals 0 and performing integer division n // equals 3, are constant time operations, or O1. Similarly, the initial condition if n equals 0 is also evaluated in constant time. Overall, the primary contributor to the time complexity lies in the number of iterations of the while loop. Now, considering the overall time complexity, the dominant factor is the while loop, which executes log_3 n iterations. Since each iteration involves only constant time operations, the total time complexity can be expressed as log_3 n. By applying the change of base formula, we know that log_3 n can be rewritten as log_10 n /log_10 3. Here, log_10 3 is a constant, so the time complexity simplifies to log n with respect to the input size. For the space complexity, the algorithm is highly efficient. It operates with O1 space because no additional memory is allocated during execution. The input variable n is modified in place, and no extra data structures or recursive calls are utilized. This means the space usage remains constant regardless of the value of the input, making the algorithm both time efficient and memory efficient. When comparing this algorithm to a brute force approach, we can see why it is significantly more efficient. A naive method might involve iterating through all integers up to n, checking whether 3 raised to the power of some integer equals n. This would require n iterations in the worst case, making it far less efficient than the logarithmic approach of the given algorithm. The logarithmic time complexity is achieved because the input is reduced exponentially by a factor of 3 on each iteration, which is a defining characteristic of logarithmic behavior. Furthermore, the constant space complexity arises from the absence of complex memory operations or additional storage requirements, making the algorithm exceptionally space efficient. In terms of best, average, and worst-case scenarios, the algorithm is consistent. In the best case, where n is already 1, the loop terminates immediately in O1. For typical inputs, the time complexity remains log n, and even in the worst case, where n is a large power of 3, the time complexity does not exceed log n. The space complexity remains O1 across all scenarios. In conclusion, this algorithm provides an optimal solution for determining whether a number is a power of 3. Its logarithmic time complexity ensures that it performs efficiently even for large inputs, while its constant space complexity minimizes memory usage. This is in stark contrast to a brute force approach, which would be significantly slower and less practical. The efficiency of the algorithm stems from the exponential reduction of the problem size during each iteration of the loop. Overall, this combination of time and space efficiency makes the algorithm both robust and highly suitable for this problem. When solving the power of 3 problem, there are several common mistakes to watch out for. First, it's crucial to handle edge cases properly. Remember, powers of 3 are always positive integers, so any input where n is 0 or negative should immediately return false. Next, be cautious with the termination condition in iterative division. The goal is to reduce n to exactly 1, and if the loop stops too early or allows n to become a non-integer during division, the algorithm will fail. Another common issue is assuming that all large numbers are valid powers of 3 without proper validation. For example, while 3 to the power of 20 is a valid result, a similar looking number like 348, 678, 4402 is not. Finally, using floating point arithmetic can be problematic. If you rely on logarithmic calculations, precision errors can creep in, especially for very large values of n. For instance, the result of log n/log 3 might not be exact due to floating point inaccuracies, leading to incorrect results. Another mistake to avoid is hardcoding a fixed range of powers of 3 without justification. If you assume the range only goes up to, say, 3 to the power of 10 without considering the problem's constraints, you might miss edge cases. Now, here are some insights to keep in mind for interviews. Powers of 3 have a unique remainder pattern when divided by smaller integers. For example, if you divide a power of 3 by 2 or 5, you'll always get a non-zero remainder. This property can be leveraged for quick validations. If you use logarithms in your solution, be ready to explain how you handle potential floating point precision errors. Iterative division is often the preferred approach during interviews because it's straightforward and robust. However, demonstrating an understanding of alternative methods, such as using logarithms or pre-computing powers, can earn you bonus points. Be sure to discuss the trade-offs in time and space complexity. For example, iterative division has a time complexity of O log n, while checking pre-computed powers of 3 runs in O(1) time but requires additional space for storage. This problem also has some related problems that you might encounter. For example, LeetCode 231 focuses on checking if a number is a power of 2, while LeetCode 342 deals with powers of 4. Of course, this problem itself, LeetCode 326, targets powers of 3. Another related problem is LeetCode 263, called ugly number, which involves divisibility by fixed prime factors. Now, let's explore some alternative approaches to solving the power of 3 problem. The preferred method is iterative division. Here, you repeatedly divide n by 3 until the value reduces to 1. If at any point n is not divisible by 3, you return false. This approach is simple and robust, but it can be slower for very large values of n. Another option is to pre-compute all powers of 3 within the constraint range, such as from 1 to 3 to the power of 19 for 32-bit integers, and store them in a set. Then, you can simply check if n exists in that set. This method is extremely fast, with O(1) time complexity, but it requires extra space for the pre-computed values. Another approach is to use a logarithmic check. By dividing the result of log n by log 3, you can determine if the outcome is an integer. This method is very fast, but it's prone to floating point precision errors, especially for large values of n. To address this, make sure you account for rounding inaccuracies when performing the calculation. Lastly, there's the mathematical modulo check. For this approach, you use the largest power of 3 within the constraint range, such as 3 to the power of 19 for 32-bit integers, and check if it's divisible evenly by n. In other words, you verify that 3/19% n equals 0. This method runs in O(1) time and avoids floating point issues entirely, but it does require pre-computing the largest power of 3. Each of these approaches has its own trade-offs, so choose the one that best fits the problem constraints and your interview scenario. Great work! In summary, we tackled the power of 3 problem and reviewed an iterative division approach. Remember to think critically about edge cases and refine your problem-solving skills. Thanks for watching, and we hope to see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!